Okay, let's look at the trend for ionization energy. So the first thing that we're going to look at is a periodic table here, and we're going to look at how the trend goes. And so ionization energy is energy required to remove an electron. So if we start out with the trend goes ionization energy increases as you go up a group, so it increases going up, and it increases going from left to right across a period. So that's the trend for ionization energy. You can think of it, if you just wanted to use one arrow, that the further to the right that you go and the further up you go in the periodic table, ionization energy increases. So a question might be, which has a greater ionization energy? If we said cesium versus lithium, you could just look at the trend and say lithium would be the right answer because it's higher up. As you go up, the ionization energy increases. Or you could have a problem like which has a higher ionization energy, bromine or potassium? And the answer would be bromine because it's further to the right on the periodic table. All right, so those are some of the types of questions that you could get. All right, but you have to be able to explain why. And so the why part is what we're going to focus on in this video. So what I would like to do is look at this picture right here, and this shows a group trend. This is group 1A here, and this is going across a period 2 with lithium, beryllium. It doesn't have all, but most of them. So the first thing to understand ionization energy, we're going to use a simplified version of Coulomb's law, which basically says the energy required to remove an electron is equal to the charge that's positive. Basically, that's the charge of the nucleus, okay, multiplied times the charge negative, that's an electron, the electron that we want to remove. So you take the charge of the nucleus times the charge of the electron, and you divide that by the distance between them. So the question would be, let's look at lithium. So if we want to remove this electron, and we look at it right here, we have to look at the nucleus. And the nucleus has 3 protons holding this 1 electron. All right? And so we look at that, and then we look at how far away it is, and then we could calculate some energy. But remember, as you go down a group, the radius gets a lot bigger. And so to take this outermost electron from potassium, it would take a lot less energy because this electron is a lot further away than lithium's electron up here. So because potassium is so much further away, it takes less energy. It takes more energy to take lithium. But you might say, well, hey, what about the protons? Lithium has 3 protons. Potassium has 19 protons. Well, the thing is, potassium's electron, this outermost electron, is affected by shielding. Shielding is when all these inner energy level electrons block the protons in the nucleus from attracting this electron. So you can think about all these electrons, these inner energy level ones, they could get in the way here, and they're going to block the nucleus from attracting this electron. So as you go down a group, the shielding effect increases. That offsets the number of protons in the nucleus. So they use this term called the effective nuclear charge. Well, the effective nuclear charge is diminished as you go down a group because of the shielding effect. So the shielding effect really is a big factor in a group trend. All right? All right, so lithium, okay, it would have a higher ionization energy for this outer electron compared to potassium because lithium's electron is a lot closer to the nucleus and it has less shielding. All right, so that's the group trend. All right, so now let's do the period trend. So the period trend is going across. If we were to start here with lithium and we compared it to like some of these going across. So once again, we'll look at this simplified version of Coulomb's law. So let's compare that. We're going to take this electron from lithium here versus one of these over here for nitrogen. All right, so if we're comparing lithium versus nitrogen going across a period. So if we look at this simplified version of Coulomb's law, if we plug it in for lithium, okay, the nucleus for lithium has 3 protons, okay? We're trying to take 1 electron, so that's like 1 minus, divide it by the distance, okay? So the distance from this nucleus to this electron, we're just going to call it a factor of, we'll just make up a number here. And we'll say it's about 1, 2, 3 units. Okay, so we'll just plug that in. I'm just kind of making that distance up. But now if we compare it to nitrogen, all right, nitrogen, if we look at it, if we did its formula, energy equals, okay, nitrogen has 7 protons in the nucleus. So that's a charge of 7. We're trying to remove 1 electron divided by the distance. Now if you look, the distance for lithium here from its nucleus to its electron, it's about that far. I'm not measuring this with anything real, but anyway, if you look at nitrogen's, it's at least half the distance. So we could put in maybe something like 1.5 here. Okay, because the distance is so much smaller, okay, the energy value is going to be a lot bigger, okay? So going across a period, there's 2 factors, all right? So let me just write it up here. So in the period trend, okay, you're going to always have to measure 2 factors. Number 1, okay, the effective nuclear charge increases. Okay, it increases because protons increase as you go across. Look, lithium has 3, beryllium has 4, boron has 5. See how you're getting more protons? So the nucleus becomes more powerful as you go across a period. Okay, the other thing that you have to think about is going across. There's 2 factors. So the nucleus gets stronger and the radius gets smaller. Radius is smaller. So because those 2 factors go together, making it as you go across, the nucleus gets more powerful, but the electrons are closer to the nucleus, so it's going to take more energy to take them. So in a period trend, you always need to mention these 2 things when you're talking about ionization energy. All right? Now, let's go back to the group trend and let's write down a couple things. So for the group trend, the thing that you always want to mention as you go down, number 1, okay, the first thing that you're going to look at is when we're talking about ionization energy is as you go down, the radius increases. The radius increases. And if the electron is further away, it takes less energy to remove it. The further away an electron is, the further away, or the less energy it takes. Now, the other thing that you want to always mention in a group trend is the shielding effect. The shielding effect, what it does is it decreases the effective nuclear charge. Okay, so you always want to talk about these 2 things when you're discussing a group trend for ionization energy. Now, the thing is, some people might say, well, hey, what about shielding going across the period? Look, shielding is never a factor going across the period because look, there's 2 electrons here that could shield this one. Look at beryllium. There's 2 electrons that could shield one of these outer ones. In boron, there's 2 inner electrons that could shield the outer ones. Carbon, there's only 2. What I'm trying to get at is that going across a period, shielding is constant. So everything here has equal shielding, so it's never a factor in a period trend. But shielding is always a factor in a group trend. All right, that's it with this ionization energy video.